The last concept we'll introduce in order to talk about covering nodes or edges in a graph is the concept of a matching. And a matching is a collection of edges, and in particular, they're ones that are non-adjacent. And another way of saying that is that no two edges share the same node. So we're not really thinking about creating paths through the network, really coming up with all of the edges that don't share any nodes together. And clearly, you could always just pick one or two, and that would be a very easy task. So the more interesting question is to construct a maximum matching where you try to pick as many in terms of number or in terms of weight of edges, so it is maximum. So the weight is maximum or the count is maximum. And if you actually are able to collect all of these edges such that all of the nodes are adjacent to some edge in the matching, then this is called a perfect matching. So that's not guaranteed that you can do a perfect matching. Some graph structures are just make it impossible. But if it is, then you have this perfect matching. And so two terms that we'll use in our discussion of how you create matchings is this idea of an alternating path and an augmenting path. And so a node is matched if it's adjacent to an edge in the matching. And so an alternating path begins at an unmatched node, and then after that the edges alternate between belonging to and not belonging to the matching. And so this is kind of an odd kind of path in which not all edges are being selected, but every other edge is being selected. And then the augmenting path is an idea that it's a path that begins and ends at an unmatched, that both the beginning and end are unmatched nodes. And the concept of a matching is certainly allowable and used in general graphs. However, it makes a lot more sense and it's very intuitive on bipartite graphs. And so the way that is interpreted is kind of, if you look at this left-hand side picture, a matching then is, because all of the edges go between nodes of type A and nodes of type B and not between A or between B, then you're really pairing. You're coming up with all of the pairings that you can make between where each pair has something in A and something in B. And again, this is the canonical kind of dance card problem where you have guys and girls on either side, and you're trying to make as many dance partners as you can. And that same analogy can be used in tons and tons of different types of problems, where the only partners that you can make are ones that have some sort of edge between them. And so in this case, the red indicates edges that are being selected in the matching. And so this is one example of a maximum matching, that out of all of the edges that are available, we select these, and this allows us to have an assignment that creates a matching in this graph. An interesting thing, one way of interpreting this is that if we think about this in the context of flows, then because we're selecting edges that have maximum weight, then even on a weighted graph, but this is still generalized as to be true on unweighted graphs, is that if we insert a source and a target node and essentially create directed flow from that source to target, then the edges that we would be picking are the ones that maximize the flow throughput from the source to the target. And so that would be essentially creating the heaviest set of edges to carry the most amount of capacity from the source to the target. And so the size of the matching, this maximum matching, is the same thing as the maximum flow that you can get, which again, remember, is the same as the cut set that you would select in order to disconnect the source and the target. So that's one way of thinking it, but there is a more efficient algorithm to do this. The more efficient algorithm in order to find maximum matchings on bipartite graphs is the Hopcroft-Carped algorithm, which runs just a little bit faster than the flow, and it centers on finding these alternating augmenting paths. And so remember, a augmenting path is one that starts and ends at a unmatched node, and an alternating path essentially alternates between having an edge out of the matching and in the matching and out of the matching and so on. And so if we combine those two things together, it's an alternating and augmenting path. This is one that qualifies, so this is a very simple one. So this has two unmatched nodes and a single edge that is not in the matching. A slightly more sophisticated one would look something like this, where we start with an unmatched node. There is an edge that is not in the matching, then an edge that is in the matching, and then another edge that is not in the matching, and then we end with an unmatched node. And so this is again an alternating augmenting path. And so we can call that our alternating augmenting path P. And so if we find one of these in our bipartite graph, then what we can do is we can actually essentially swap it with this edge that's in the matching. So what ends up happening is we take something called the symmetric difference, which says that we keep all of the edges in our current matching M and the new alternating augmenting path P, but not the ones that are in both. And so, for example, this edge here is one that's in both the alternating augmenting path and the matching. And so for that reason, it isn't here in the result. We no longer have it in the matching, but we keep this, keep these two new edges. And so you can see that we originally had a matching that had one edge, so it had weight 1. And so now we have a matching that has two edges, so it has weight 2. And so by doing this symmetric difference update, we actually increase the matching by 1. And so the same ideas would hold if it was weighted. And so we won't go into showing this, but it can be shown that essentially the symmetric difference between your current matching and an optimal matching, note that it is possible to have many different optimal matchings, but the difference between a current matching and an optimal matching is a collection of alternating augmenting paths. And that means that if you no longer have any alternating augmenting paths, then you must have reached an optimal matching, because then there would be not any paths that you could swap out. And so that kind of gives you an idea of matching. The same algorithm can be run on directed and undirected graphs by doing a transformation of the graph, and we'll talk about that later on in the class.